Hi everyone, I am Neel. I am a PhD student at the University of Portsmouth in the UK. My supervisors are Johannes and Kazuya, and my talk is about the impact of theoretical priors on cosmological modified gravity constraints. Now, I want to understand the nature of dark energy, and there are three big questions about dark energy. Depending on whether you are a theorist, a phenomenologist, or an observer, you would be most interested in one of these three questions. And the objective of my research and this talk is to show the connections that exist between these three perspectives. I will start with the theoretical question, which is what is the fundamental field theory behind dark energy? So I am working in the framework of the effective field theory of dark energy. This is a well-motivated class of models where the role of dark energy is played by a single scalar field. The only other thing that is assumed is the symmetries of the cosmological background. The EFT framework combines these minimal assumptions with a general scope, and it allows for all couplings of the scalar field to gravity that are compatible with the assumptions. Also, when we make the assumptions of the fourth bullet point about second order derivatives and Lorentz invariants, and when we are concerned only with cosmology, the EFT of dark energy is equivalent to Horn-Disley gravity, which is a well-studied class of modified gravity models. So what does this look like? We can get to the EFT of dark energy by slowly adding things on top of general relativity. We first add a simple scalar field with a simple kinetic and potential term. This gives us the freedom of the equation of state of dark energy. Then we can make the kinetic term of the scalar field more interesting. This gives us a new function called alpha k. We can also couple the kinetic terms of the scalar field and gravity. This gives us a new function alpha b. We can also let the gravitational constant or the Planck mass vary with time. That gives us the function alpha m. And finally, we can also let the speed of gravitational waves differ from the speed of light. That gives us the function alpha t. So these five functions of redshift are the degrees of freedom in the effective field theory of dark energy. It turns out that for linear perturbations in cosmology, the two functions that are the most relevant are alpha b and alpha m. So these are the two functions that I will vary and that I will constrain with data. I will focus less on the other functions. So now I'll talk about the phenomenology of dark energy. Dark energy interacts gravitationally, and to understand its phenomenology, we need to remember three things about gravity. The first is that in GR, there are two gravitational potentials for linear perturbations. And the next two things are about the famous statement, space-time tells matter how to move, which is captured by the geodesic equation, and matter tells space-time how to curve, which is captured by the Poisson equation. It turns out that relativistic and non-relativistic matter are sensitive to different combinations of the two gravitational potentials in the respective geodesic equations. And so they feel different accelerations. And we use this fact to write down two corresponding versions of the Poisson equations as well, which are shown here. And these two new functions, mu and sigma, characterize any deviations from GR. In GR, both of these functions would be 1 at all redshifts, but in modified gravity, they can differ from 1. And mu affects the clustering of matter, which we would see in galaxies and large-scale structure. Sigma affects the trajectories of photons, which we would see, for example, in the CMB. So there is also a third function used in the literature, which is called gamma. It is related to the ratio of the two gravitational potentials. And it is defined in this way because in GR, these two potentials are equal in the late universe regime. But in modified gravity, they can be different from each other. Out of these three functions, only two are really independent, and we can derive any from any two of these functions, we can derive the third one. Finally, I'll now talk about observational constraints. First, let me mention what data I am using. Since the phenomenology that we can get affects both clustering and lensing, it is very useful to combine probes of clustering and lensing. So here I will be using the CMB, redshift space distortions, and the integrated Sachs-Wolf effect as my probes of perturbations and of clustering and lensing. And as probes of the background expansion, I will be using BAOs from EBOS and supernovae from Pantheon Plus. Now, there are two main approaches used in the literature to constrain dark energy and modified gravity. The first is the phenomenological approach. Here we start directly with the Poisson equations for light and matter. So these two equations. And here we forget everything I said before about the EFT of dark energy. We just take these two equations, we directly parameterize them, and we constrain mu and sigma with data. The second approach is the more theory-informed one, where we start with an underlying field theory, as in the effective field theory of dark energy. We parameterize alpha b and alpha m, and then we constrain the alphas with data. And then we derive the Poisson equations of the theory. From them, we infer mu and sigma, and thus we also infer the constraints on mu and sigma from the data. And I'm interested in how the constraints on the phenomenology compare between these two approaches. I will do this comparison by reporting constraints on the present day values of mu and sigma, which are denoted mu0 and sigma0. So practically what I do is in the phenomenological parameterization, I start with the mu and gamma functions, and I need to assume some form for the time dependence because we cannot constrain arbitrary functions of redshift with a finite amount of data. This here means that they are proportional to omega dark energy, which is the fractional energy density of dark energy. This ansatz is widely used in the literature, and its motivation is that simply that since this is an effect related to dark energy, so we just make it proportional to the energy density of dark energy. It's not a very strong physical motivation, but this is still a widely used ansatz in the literature. Here we have the relation between gamma and sigma, from where we derive sigma at all redshifts. From mu and sigma, we get the Poisson equations at all redshifts, which gives us predictions for large scale structure and the CMB. Then we can constrain them with data. And for the theory-informed parameterization, the story is similar. But instead of mu and gamma, I start from the underlying field theory, where I parameterize alpha b and alpha m. Again, I make them proportional to omega dark energy. But the other steps of the process are the same. Now we derive the Poisson equations from the alphas instead of directly parameterizing mu and gamma. So we have our Poisson equations, which means we have our predictions for large scale structure in the CMB, and we can constrain things with data. The question is, how do the two approaches compare? And this is what the comparison looks like. We see two different posteriors here. The wider posterior is for the phenomenological parameterization, and the tighter or smaller posterior is for the EFT of dark energy parameterization. It turns out that in the EFT of dark energy, you cannot have like any given value of mu for any given value of sigma. There are some correlations imposed between mu and sigma, simply because they are derived from the underlying physics of a field theory. Practically, this leads to a theoretical prior on mu0 and sigma0, and that is what gives us the tighter constraints on these two parameters. Now, Constraints on the present day values of mu and sigma are not the only way to compare the phenomenology of the two different approaches, the phenomenological and the EFT approach. We can also compare the time evolutions of mu and sigma across the two approaches. So here I am showing for a few different cases. I am showing the time evolutions of mu and sigma in the EFT approach when they are derived from an EFT, which are the solid lines, and I'm comparing them with when they are just parameterized directly phenomenologically, which are the dashed lines. And we can see that there are some cases like these orange lines here, and also this purple line down here. So there are some of these cases where the evolution is pretty close. But there are also some cases where the evolution is actually quite different across both of these models, which have the same values of mu 0 and sigma 0. As you can see towards redshift 0, they are both going to the same value. But even for the same present day values, it turns out that we can sometimes find very different evolutions of the phenomenology between across the phenomenological and the theory informed parameterizations of modified gravity. So this was about a theoretical prior on the phenomenology of modified gravity coming from the EFT of dark energy. The next step that we can take is to impose theoretical priors on the EFT of dark energy itself. And I will talk about two such priors. The first one is about the background expansion. Now, typically in the literature, when the EFT of dark energy is constrained, a lambda CDM expansion history is assumed, meaning that the equation of state of dark energy W is set to -1 at all times. But now, because of the DAISY results, we have a very good reason to explore backgrounds beyond lambda CDM and wonder what happens when we vary the background expansion as well. And the question that I am asking is, are the constraints on the modified gravity perturbations in the EFT of dark energy robust to the constraints on the background expansion history? And here is the answer. Here I am comparing constraints on mu 0 and sigma 0 coming from the effective field theory of dark energy across two cases. One where the background has been fixed to a lambda CDM like background with W equals -1, and one where the background is varied and marginalized over using the W0 WA parameterization. And from this plot, we can see that the constraints on perturbations are actually robust to whether we fix the background or if we vary it and marginalize over it. Next, I'll talk about a different kind of theoretical prior, which was first derived by Creminelli and other authors in 2019. This is about the stability of the theory in the presence of a background of gravitational waves. Again, we have very good observational reasons to now consider a background of gravitational waves because we know that there are binary black holes merging all the time in the universe. And we have also detected a stochastic gravitational wave background from pulsar timing arrays. Now, here the theory states that for the theory to be stable in such a background of gravitational waves, with another extra assumption here that the speed of gravitational waves is the same as the speed of light in the theory. In this setup, the only kind of coupling to gravity of the scalar field that is allowed is a purely conformal coupling. Now, practically what this does is this condition reduces 2 degrees of freedom to 1 because it imposes a completely deterministic relation between alpha b and alpha m. So what does this look like for the constraints on mu and sigma? This is what it looks like. Here we have the constraints from the more general EFT of dark energy compared with the constraints where we have imposed the theoretical prior of stability in a background of gravitational waves. Since we have reduce 2 degrees of freedom to 1 in the theoretical prior, we will get a 1D posterior between mu and sigma, which is a drastic change in the shape of the posterior coming from the theoretical prior, and this is what the comparison looks like. We have a few other results mentioned here, which I did not get time to speak about in this talk, but we can compare different time dependencies because what I have been using here, the proportionality to omega dark energy, is not God given. What we have done in the paper is we have compared it with another widely used time dependence, which is where the effects are proportional to the scale factor. We can also vary the speed of gravitational waves because the speed of gravitational waves on cosmological scales can be different from the speed on the scales of LIGO, which has been constrained to be very close to the speed of light. The other thing here is a theoretical prior related to shift symmetry in the EFT of dark energy. It was first derived by Dina Trekova and other authors. And the last thing is, this is an observational rather than a theoretical question. And this is about the degeneracy of modified gravity constraints with the A-lens nuisance parameter in the CMB. Let me conclude now. What I have conveyed in this talk is that we need to connect the perspectives of theory, phenomenology, and observations to understand the full picture about dark energy. And for the theory, the effective field theory of dark energy is a well-motivated class of models that has minimal assumptions and still allows for a variety of phenomenology. We can use two approaches to constrain dark energy and modified gravity. We can either directly parameterize and constrain the phenomenology, or we can parameterize and constrain the EFT of dark energy and derive constraints on the phenomenology from it. I have shown how the constraints compare across these two cases. And then we can take theoretical priors to the next level by applying or relaxing theoretical priors made on the EFT of dark energy. So that's all I wanted to talk about. Thank you very much.